Hello everyone. So we are back again. What we are discussing about the dispersion relation of Langmuir waves, the high frequency electrostatic waves. So we let us try to understand some more insight about this dispersion relation. So what we did in our previous class is that we found that this GVX is basically consists of two terms. One is ion term and another is electron term. And for high frequency electrostatic waves, we are in a location where these ion terms contribute very negligibly compared to the electron terms. So we can neglect this one and we can do with this term alone. So now in this actually we will try to understand some more insights about this dispersion relation. So for that actually we will try to get the properties of this GVX. So when you integrate this GVX over the whole range, it gives you 1. So when this is the case, this integral GVX and DVX equal to 1, so this essentially tells you that GVX is the probability of finding the particle within Vx and Vx plus dVx. Then only when you integrate over the whole range, this gives you 1. So GVX is kind of probability, and this integral value is equal to 1, we should remember for rest of our derivation. But once for all, we should try to convince ourselves, we should make ourselves convinced that this integral is really equal to 1. So how to find that? We get into this integral and we put the value of GVX, as we have already seen that it is consisting of two parts. One is your ion term, one is electron terms. And for the derivation of our this high frequency electrostatic waves, and for most of the regions of this function, this ion terms contributes very negligibly, and we can approximate this by this term alone. And if we do so, then we make the substitution like this: x is equal to bx square by twice b square to get the integral done. And if we put so, then dx comes like this, and we substitute over here for this dvx and this integrand, this exponent value, and we get this is the expression. So you remember here we are integrating our minus infinity to plus infinity range, and this factor 2 appears because we have now changed the limit from 0 to infinity. And finally the integrand actually appears like this when you make this substitution. So you can verify this, and this 1 by pi root pi factor is there, and the rest of the things you can well recognize that it is nothing but this is gamma function, gamma half, and gamma half is just root pi. So root pi cancels and we get 1. So to get this integration done, there are n number of ways to do it, but we have done in a very smart way by using the gamma functions, and you are now convinced that this integration is really equal to 1 over the whole range. So once we have done this, we remember this property of this integration, then whenever we do the integration over the whole range, this will give us the value 1. Apart from this, if we do this integration multiplying by Vx, because Gvx is a this is a symmetric function, and you are multiplied by Vx, it becomes asymmetric, and when you integrate over the whole range, and you can understand, then this will give you 0. So this is a very known fact to all of us. So this integration is 0, there is no doubt about that, and we remember this also. And the other integration that will require frequently in our derivation later on, that Vx square multiplied by Gvx, then integrated over the whole range over dvx, and what is the value of that? Then I guarantee that that will be equal to V square for the kind of distribution we are handling. And we do it once to convince ourselves that it is really show when we integrate Vx square over the whole range, it gives us V square. Okay, so that is I integration over minus infinity to plus infinity Vx square Gvx dvx. So we get take this thing like this. We can put the value of the GVX over here, and we make the same substitution as we did earlier, that x is equal to Vx square by twice V square, then dVx comes like this, and you put these values over here. See, we have Vx square by twice V square over here, and then again the exponent value is the same, and we can replace dVx like this. So when this is x, so this is minus x, and dVx comes from here, I get an expression for the integration like this one. Now you remember here that this integration is minus into plus infinity. So when we take into 0 to infinity, we take a factor of 2 over here. Okay. So then you now can understand, recognize what is this integration is. This is nothing but what is that? Gamma 3 half. And what we have got outside is 2v square by root pi, and gamma 3 half is nothing but half gamma half. So half factor is there, and then gamma half is root pi, and root pi cancels, and ultimately you are left with v square. So we have now very much convinced, that this integration is nothing but v square. So what we are getting? Three integral values. One is GVX dVX integration over the whole range, that gives you 1. Then Vx integration over the whole range, Vx into GVX, that is equal to 0. And when you do similar integration on Vx square, then GVX and dVX, that gives you v square. So we remember this integration values for remaining of our derivation when they appear. So what we are now left with? We are now left with the dispersion relation for electrostatic waves like this. This is the case. And what we are now going to? We are going to get this dispersion relation for high frequency electrostatic waves, these Langmuir waves. So when omega by k is much greater than thermal speed of the electrons. And here, when you are getting this dispersion relation, general dispersion relation, we are now very much clear about how this goes. Okay. So to get this thing done, what we need to do? We need to simplify it further. And to simplify, we as a physicist, we have the tools to expand it and to extract, so that we can extract some insight about the relation that is lying within this. Now, to expand, we need that omega by k should be much greater than Vx, so that this Vx by omega by k becomes a small quantity. Okay. So that is the condition for this for the Langmuir waves, the high frequency electrostatic waves. So we can expand it, and we will do so, but later on. But now what we'll do actually, we do your integration by parts. So if we do that, then we come over here, and then this first into integration of the second minus differentiation of the first, differentiation of the first into integration of the second, then whole integration. Okay. So the first one gives you a bare GVX. This GVX, when you put the limits of plus and minus infinity at both the ends, it goes to 0. So this term gives you simply 0. And the remaining one comes over here. So from this dispersion relation, which is like this, you now get reduced to an expression for the dispersion relation for high frequency electrostatic waves, where you are getting this value. Okay. And we remember again that we are considering the case where typically omega by k is much greater than Vx. Okay. For all Vx they are under consideration. So if that is the case, then what we can do actually, we can expand this value, expand this part, and we can get some more information about the dispersion relation. So if you do that, then we usually keep up to first order term, but here we are intentionally keeping up to the second order term, this one. This is required because if we really want to get some insight about this dispersion relation, we will see that this term is helping us. So now we have expanded it, and with the condition that Vx by omega by k is a small quantity, and that is the case for the Langmuir waves for all this Vx that is of interest. And then what we are getting, we are expanding this. So the first integration coming as integral of gvx dvx over the minus infinity and plus infinity range. And then the second one is coming is as twice k by omega minus infinity plus infinity vx gvx dvx, and then the third one is coming as vx square gvx dvx integrated over minus infinity plus infinity. Now you can remember that just a little before we have got the value of all this integration. The first one gives you nothing but the probability, that is 1, and the second one is 0 because it is an asymmetric function. The third one gives you simply v square. So what we are now getting is this expression for the Langmuir wave dispersion relation. So now you see that what in the interest of getting some insight about the dispersion relation, we started with a general dispersion relation which was looking awkward, and then we just did some integration by parts and put the values of the properties of gvx, and we could simplify this to this one. This was still not very much clear about the insights what is there inside the dispersion relation. Now we have reached to an expression which is just containing only 3 terms. So this is now looking very attractive because we will be able to extract some information about the kind of dispersion it supports. So what we are left with, 1 minus omega square by omega square minus thrice k square v square omega square by omega to the power 4. Now the thing is that it is still not very clear. It is keeping some quantity to the power 4, and this is multiplication of 3 terms over here. Not very much clear, but physicists always have some clever means to extract a simpler expression out of a complex one. So we will try to do that, and you just follow the logic that I am applying over here. Now you know that this is arising as a first order term, this is arising as a second order term. Okay, so second order terms are always, this is small, although we have not neglected it over here. So just for the timing, let us neglect it. Then what is coming? Omega square equal to omega square, but that is not attractive because we know that this is a dispersionless relation, but we know that omega will be close to omega e, but it will not be exactly omega e. But for approximation purpose, we can always put omega square is equal to omega square. So in the second order term, we will just use this relation, that is omega e square equal to omega square. So in that way, we will be able to cancel one omega square term. So omega to the power 4 is equal to omega square into omega square, and 1 omega square we just cancel with omega e square. So in that case, you just left with thrice k square v square divided by omega square, exactly this term. So we have done some approximation, neglecting the second order term, but finally we are keeping this term over here, and we have used just that approximation, and we are getting an expression of this kind. So now we have reached to a remarkably simpler and very elegant expression for the dispersion relation for Langmuir waves, that is equal to omega square of the order of omega square plus thrice k square v square. So this is something very simple and understandable. We see that when your k is very small or b is very small, then omega square equal to omega square. So that is the wave is just dispersionless. But when k is large, b is large, then the dispersion of the wave is appreciable. So you just now Remember, you just now try to understand that we started with a very awkward kind of expression for the general dispersion relation. Then we made the approximation and reached a simpler expression, and then we expanded it, did the integrals, and finally we are able to reach to an expression which is quite tractable and gives a clear insight about the dispersion relation for the high frequency electrostatic waves that is possible. So, what the dispersion relation now gives? It gives the relation about how the wave, this frequency actually changes depending on k and v. So, the dispersion relation describes how the phase velocity and group velocity vary with wavelength. For Langmuir waves, dispersion relation plays a key role in understanding the wave propagation, stability, and energy transport in plasmas. So, at small k value, phase velocity omega by k is very large, but the group velocity d omega by dk can well be small. So this means that wave packet is spreading out. Wave packet is spreading out, as we can see here that this is the way it spreads out, because you know that different wavelengths having different k value, because you know that inverse relation between wavelength and the wave number k. So different wavelengths are now propagating at different speeds, but their group velocities are not changing, or they are remaining the same or small. So that's how they are spreading, but the group velocity is not changing. So this affects signal transmission in plasma based communication like space plasma, fusion, and makes it harder to localize the energy due to this kind of spreading. The dispersive term comes from electron pressure response also, because you know that higher temperature, so V will be very high, and when the shorter wavelength means K is very high, so thermal motion of the electrons matter dispersion of the electrostatic waves. So now you can understand that this term, dispersive term, becomes significant when K is large, that is shorter wavelengths, and when V is high, that is at higher temperature. So that is how the dispersion relation for the electrostatic waves can give us the information about how the your Langmuir waves can affect the energy transport in plasma. Now, not only that, this Landau damping, what we have seen in our previous classes, it is a form of collisionless damping. Why it is so? This is because we started with collisionless plasma, Blasov equation, and that resulted in that this Landau damping kind of thing. So in case of collisionless plasma also, the electrostatic waves can undergo damping, and that is what we have understood over there. The damping depends on the slope of the electron distribution near the phase velocity only. Okay. So the dispersion changes phase velocity and thereby dictates which set of electrons will participate in the damping or amplification of Langmuir wave. So just closely observing the dispersion behavior, we can infer about the plasma parameters like temperature, density, thermal population, and whether the distribution is Maxwellian or non-Maxwellian, or if any presence of energetic beams inside the plasma is there. So what we can know, we can from experiment we can just check what dispersion behavior the plasma is offering, and from there we can get idea about the plasma temperature, plasma density, the non-thermal population, or the Maxwellian and non-Maxwellian features, or if there is any energetic beam present inside the plasma. So understanding growth and decay of electrostatic waves in plasma is also crucial for understanding the instabilities. Now this is one example just to make the concept complete, and you will see that this has really some importance in very high-end technological areas. So you know that fusion, inertial fusion. So this is one, the pellet is here and the lasers are ablating the periphery of that pellet, and outer layers just becomes plasma and rapidly expands outward. That way, just because of that rocket action, the inner fuel gets compressed inward and causes fusion. Now the fact is, the intense electric field of laser not only heats the pellet but excites Langmuir waves. So understanding the dispersion becomes crucial if you want to really manage the technologies. So that is just one example. There are numerous examples where this wave propagation becomes very much important. So what we started with, actually we started with our kinetic theory, then we integrated our different we got that plasma kinetic equation, and we took moments of that plasma kinetic equation of various orders, and we are trying to get the conservation equations. So what we did in between, we tried to understand the this presence of electrostatic waves in plasma. Because of the mathematical complexity, we tried to elaborate it in detail, and we tried to get some more insight about the behavior of this electrostatic waves in plasma. Now we are coming back to our fluid model again. So we again start with our this thing basic equations. So for this plasma kinetic equation, we have obtained this species conservation equation, which looks like del ns by del t plus divergence of Vs/Ns equal to integration over del Fs by del t into dV, and this term actually we told that it is equal to 0 because this is giving you the change in the number density over time within the your phase element, phase volume element. So we considered that the number of particles which are coming within the element is same as the number of particles which are going out. So eventually this there is no change in the number density, so this is giving you A0. So this is fairly a good approximation, and with the help of that we got the species conservation equation over there. Okay. Now once we get that, then we can get the charge conservation equation or the current continuity equation from there. Okay. So what we do, actually we take this expression for ions. So it comes like this, del Ni by del T plus divergence of Vi Ni, this is for ions, and for electrons what we get, this just we replace this S by E, and we get del Ne by del T plus divergence of Ve equal to 0. Okay. Now what do we do? We multiply this by Qi on both sides, so we get this expression del T of Qi into Ni plus divergence of Vi into this should be actually Qi, not Q. So Qi Ni, that is equal to 0. Then plus we have this one, this we multiply by QE, so this becomes del QE into Ne divided by del T plus divergence of QE, you multiply over here, then it becomes QE into this is VE into Ne. Okay, so this just comes over here and that is equal to 0. Now what we are going to do, we are adding these two equations together. Then what we are having, this is del T into this QI plus this is QE this comes over here, and then within the divergence what you are getting, this is QI VI plus QE V, so that is equal to 0. Now we remember that how the charge density is defined. This is sum over all the charges. Ni is the ion density and Ne is the your this thing, what is that, electron density. So this should be QE, not Me. Okay, so this should be QE. So this is QI plus QE and Ne, you read this as QE, not Me. So you get the total charge density. And then current density, how do you define? This is J is equal to NeV. So this is the number density of ions, this is velocity of ions, and this is charge. So this is giving you the current due to the ions, this current due to the current density due to the electrons. So we now put these values into this one and this into this one, and what we get actually, del rho C by del T plus divergence J, that is equal to 0. So what is this? This is nothing but the your current continuity equation. So in this fluid model, we earlier obtained our species conservation equation, and that was del Ns del T plus divergence Psns, that is equal to 0. And we have used the same species conservation equation. We wrote this equation in terms of ions and in terms of electrons. We multiplied by charge of ions and charge of electrons like this, and then we added them together, and we, as per our definition of charge density and current density, we are able to write this equation in terms of this current continuity equation, that is del rho C by del T plus divergence of J, that is equal to 0. So our fluid model is now able to give the species conservation equation and charge conservation equation from the 0th order moment. Okay, so from the 0th order moment we are able to get the current continuity equation. Now we'll go for the momentum conservation equation. So how do you get it? As we told earlier, that the first order moment of the plasma kinetic equation in the velocity space will give us the momentum conservation equation. So this is obtained by multiplying the plasma kinetic equation by V and integrating it over the velocity space. So what was our plasma kinetic equation? So del D of Vs Fs into dV, then this V Gradx term, then V your acceleration into Gatvey term, and then we had this collision term on the right side. Now what we plan to do, we want to take the first order moment, so this yellow highlighted V is coming over here, we are multiplying, and then each term is multiplied and we have done the integration. Okay, and what it does actually, it will finally give you this expression, and how we get this expression will come into our next class, and we'll study this in more details there, and it will be a bit complex, but I assure you that we will be able to extract the physics behind this equation from this, although it will be looking a bit awkward for the time being, but finally the expressions that will get extract out of this equation will be very beautiful and very significant and very useful. So much this time, and we will meet in the next class. Thank you.